All right, so in the previous video, we looked at our planar truss and we solved it out using a method of sections going directly to our area of interest. An alternative to that is to use the method of joints. Now, the method of joints is particularly useful if you want to resolve all the internal forces for the entire truss, because you work pedantically from one end or the other or both towards the center and go from joint to joint and resolve all of the internal forces. So I've brought up our planar truss. I'm going to be using exactly the same truss so that you can go back and forth and compare, if you will, in the last video. And I'll put a card up here so that you can go back if perhaps you didn't see that video. The first thing I did was resolve the reaction forces at the reactions. It's absolutely imperative when you do a truss that you resolve the external forces before you try to go on and to resolve the internal forces. So if you need a little bit of help with that or you're not familiar with it, it's repeated up here, but I'm not going to go through that. We're going to take that as our starting point, the method of joints. I'm going to work pedantically left to right. So I'm going to start at joint A, which is the pin support down at the bottom. I've drawn out my pin. And now what I need to do is I need to put all of the forces that are acting on that joint on the diagram. So I'm going to start off by putting on my reactions. And we have RA, and we know that is 2.111 kilonewtons acting up. And we have RAX, sorry, the last one was RAY, it wasn't that precise, and that's 1 kilonewton. And so those are the only two forces we know, and we can see those on our free body diagram. But what we have to do is we have to add the internal forces that the joint or that the members are pushing or pulling on the joint. Remember, a truss is only able to support axial load because of the nature of the pins in the joints. And so it will always either push or pull in line with the member itself. So I'm going to go ahead and draw in our FAB roughly in the direction that it comes from. And I will label that FAB. And then FAE down here. The next step that I have to do is basically to use my equations of static equilibrium to resolve equilibrium at that joint. And in that way, I should be able to resolve for those two forces. So let's start off. We'll just go sum of the forces in the y direction. And I'm going to use positive up the whole way. So we're going to do this a whole bunch of times. So I'm not going to write it in every time. That is equal to 0. So if I look at the forces acting on the joint, we have 2.111 kilonewtons, which is that reaction AY. And we have a component of FAB acting down. Now, so what we have to do, first off, it's acting down, so it has to be a negative, but it is a component. And the one thing that I want to remind you of is that we do know the geometry of this force, and that it is 3, 4, and 5. And because the force must align with the member itself, its components, its XY components, must follow those ratios. And so we can use that to our advantage. Alternatively, you could resolve this into thetas and use your sine and cosines to get it. But if you have those ratios, quite frankly, it can be a lot easier. So this is the vertical component because we're in the y direction. So that would be 4/5 of FAB. So minus 4/5 FAB. Now it's worth pointing out that I chose the vertical direction first because I only have one unknown component in the vertical direction. So I knew I would be able to resolve it directly. Had I chosen the x direction first, I would have the x component of FAB as well as FAE to deal with. And so I would end up being in a back substitution situation. It would just be a little bit less efficient and not quite as effective. And so I can resolve this. So that tells me that FAB is equal to 2.639 kilonewtons. And of course, what we have to do is to know whether it is in compression or tension. Now, I drew this force so that it is pushing on the joint, which is to say the joint would also be pushing on the member. So with a positive number, I drew it in the correct direction. If it is pushing on the member, that means that the member is in compression. Now we can go ahead and resolve the sum of the forces in the x direction, set it equal to 0, and we have 1 kilonewton acting to the right. Again, I will use the sign convention throughout. Acting right will be positive when I do this. And that means we need to take away FAE, but we also need to take away the x or horizontal component of FAB. So that would be, and again, I'm using the arrows as I drew them to tell me whether it's positive or negative. So that would be the horizontal component, which would be 3/5 of FAB using that geometric relationship. So I substitute in for FAB 2.639 kilonewtons. And so with that, we can resolve our force AE will be equal to negative 0.583 kilonewtons. Of course, the negative sign simply tells us that we chose an assumption for the direction of FAE, which is opposite to the reality. So the way we drew it, the member pushing on the joint implies the joint pushing on the member would put the member in compression. But we got a negative number, so we actually know it's the opposite. And so that would put the member in tension. Now, it's always a challenge with the bookkeeping. The negative sign, because of the way it's drawn, is associated with the way the arrow is drawn. I'm using what's in brackets to describe that to demonstrate that I understand that this means that it's in tension and putting it in tension. I'm not implying that it's a negative tension, i.e. in compression. So a little bit of potential confusion there. So I just wanted to make sure that that was obvious. So let's keep going then. We got a few joints to get through, so we want to keep on moving. So we're not here all day. So we have joint E. Doesn't matter, you can go joint E, you can go joint B next. Sometimes you select a joint and you find you have too many unknowns and not enough equations, and so you just follow the other path along, and eventually you should find that they all get down to a point where you can resolve them. So we have joint E. So I'm going to draw the forces coming in. We have three members coming in at joint E. So to start with, we have FAE. Now we know it's coming in as tension. So we should probably draw it in as tension so we can use a positive number there. So I'll draw that there. So that's FAE, and we know that's equal to 0.583. We want to write it down so we get the sign correct when we draw the direction arrow. I'm going to draw EF, going off to the right, and we have FEB. So with that, we can decide which one of our equations of static equilibrium to apply first. It doesn't really matter. We have two unknowns, one in the y, one in the x. So let's head off. I'll do sum of the forces in the y direction equals 0, and that's equal to FEB. And thus we know FEB is equal to 0. So neither tension nor compression. And we can talk a bit about the configuration of the joint where it was pretty obvious that FEB would be equal to 0 unless there was an externally applied force at joint E specifically. And sum of the forces in the x direction has to be equal to 0. So in this case, we have negative FAE, which we have 0.583 kilonewtons, and plus FEF. So FEF has to be equal to 0.583 kilonewtons. And we've drawn that to indicate tension. So we can identify it as tension here because we got a positive number. So again, I'm going to keep on going here so that we can get through this problem without taking too long. So I look at joint B, so let's get our external forces. So we have the force AB, which we know is in compression positive, so I may as well draw it to show compression. So we can use it. And so that's FAB is equal to 2.639 kilonewtons. We have EB, and we know it's equal to 0, so that's FEB. And then we have BF. FBF and FBC. So let's resolve the sum of the forces in the y direction. Of course, has to be equal to 0. So in this case, we have the vertical component of FAB, which we know to be in the 4/5 of FAB itself. FAB is equal to 2.639 kilonewtons. I've drawn it positive up, so I'll keep it positive here. And then I've also drawn FBF is positive up, and we want the vertical component, which is also 4/5 of FBF. So that resolves FBF to be negative 2.639 kilonewtons. And because we drew it as compression positive, we know that this member is actually in tension. Now we carry right on. Sum of the forces in the x direction equals 0. And we have our x component of FAB. So x component is 3/5 of FAB, which we know to be 2.639 kilonewtons. That's positive right, so we're good. And then we've drawn FBF pointing to the left, so we have to subtract its horizontal component, or 3/5 of FBF, and FBF is a negative 2.639 kilonewtons. And then we have to subtract from that FBC in its entirety, and that allows us to resolve for FBC is equal to 3.166 kilonewtons, which we see is in compression. So 2 more joints to go. We're almost there. Don't despair. Hopefully you're not find yourself jumping through using that 15-second forward all the time, although it's a very useful thing to do. So we'll jump on to joint C. So FBC, which we know is in compression. So I'll draw it in compression. So that's FBC, which we know is 3.166. We have the externally applied force of 1 kilonewton being applied. We have FCF, which I will draw here, FCF, currently unknown. And finally on the diagonal, put that in here, we have FCD, which is currently unknown. With 2 vertical components and only 1 horizontal component, I'm going to choose to do the sum of the forces in the x direction is equal to 0. And so we have FBC, or 3.166 kilonewtons minus 1 kilonewton for the externally applied force, and minus the horizontal component of FCD, and the horizontal component follows 3/5 of FCD. So we're able to resolve for FCD as our only unknown in the equation, equal to 3.166 kilonewtons, which we see is compression. Now, sum of the forces y direction equals 0. So we have FCF acting positive up. We have the vertical component of FCD, or 4/5 FCD, and that's all we have. FCD, we have can substitute in 3.166 is kilonewtons, which is known, and so we can solve for FCF as negative 2.889, which is tension, because I've drawn it as compression, but we got a negative number, so we see that it is in tension. So we're going to finish off. We have one more to resolve, so let's look at joint D. At joint D, we have FCD, and FCD is in compression, so I'll draw it in compression, and has a value of 3.166. FCD equals 3.166 kilonewtons. We have FFD, don't know what it is, so we'll just draw it in here, FFD. And finally, of course, we have our reaction force, which is vertical, and that's equal to 889 kilonewtons. And really we have the one unknown, so to resolve it, we do sum of the forces in the x direction is equal to 0, which is the horizontal component, or 3/5 of FCD. Substitute in for FCD, 3.166 kilonewtons, and we add to that FFD, and we get FFD is equal to negative 2.166 kilonewtons. We've drawn that as compression. We got a negative sign, so once again, we know that to be in tension. Now that resolves all of our members for their internal forces. Certainly a question like this begs to have some kind of a summary to wrap it all up and make sure that it is adequately annotated, so we could do something else. The other thing you might want to consider is we never resolved joint F. And by going full circle, what it does is it allows you to check to make sure that you haven't introduced an error anywhere. So when you do the sum of the forces in the x and the y direction about joint F, you should be coming to 0, of course, in all those instances. And if you don't, then you know that you've got some kind of an error in your solution, and you can go back and fix it. So that's about it. From here, there is a bookkeeping shortcut method, if you will, that I was shown a long time ago. It works well for me. So I'm going to put a link to the video here at the end. I'm going to go through this same problem using that sort of graphical layout shortcut method, which works for me now, and I'll talk to its advantages and disadvantages in the next video. So if you want to see it, that's great. If you don't, you want to go back and look at the method of sections, because you might not have seen that yet, I would encourage you to consider doing that. So thanks for this. I hope that was helpful to you, and we'll see you on the next one.